This is part of a series on data structures. In this video, I want to talk about data structures that handled ordered collections of data. Things like arrays, lists, stacks, and queues. Why do we need multiple ways? Because they use data differently, and different techniques are good for different applications. Some modern programming languages like Python don't exactly have these specific structures, but they have structures built on them and employ a lot of these same concepts. Some people find it helpful to know what's going on under the hood, and just seeing the considerations that are behind the need for all these different data structures can help you apply those same kinds of considerations in other contexts. Let's start with arrays. You've seen in previous videos that arrays are ordered data of the same type, and that the data is stored in a chunk of adjacent memory. One upshot: to work, there has to be enough empty memory, and it has to be physically next to each other. It's not enough for there to be the right amount physically distributed around the RAM. Modern systems tend to have tons of memory, so this constraint doesn't hurt us, but it used to be a major issue. I'm not going to squeeze the whole thing onto this slide, but let's look at the first part of the quick brown fox jumped over the lazy dog. We just get the quick boo. The memory will have an address. It could be anything. It doesn't matter, so let's just call it n. Each item in the array has an index starting with 0. Because the memory is an adjacent block, we can jump anywhere in the array with simple math. Just multiply the size of the data type by the index and add it to the starting memory location. You don't have to memorize any of this. Just think about it. It's a simple equation. Multiplication, addition. It doesn't matter how big the data type is. It doesn't matter how many items are in the array. One equation with a single piece of multiplication and addition gets you anywhere into the array almost instantly. But what happens if you make a mistake in an array? When we're typing, we just stick a cursor in there and start over. But an array is a fixed clump of memory. If we had the wrong letter, but with the right size of an array, it would be easy to replace it. But since we left something out, it's shorter than it needs to be, and the memory allocated for the array isn't long enough. So here's what happens under the hood if we have an array like this. We've got a variable pointing to it. I'm going to call it my sentence again. And the first thing we're going to have to do is find some empty memory. That's the new size. Then we have to copy over the first part. Then we have to add the new letter. Then we have to copy over the last part. And then we have to move the variable to the new address. So arrays are very fast to access, no matter how big they are, but they're extremely slow to edit. Also annoying. So let's talk about lists. A list is an interface. That means it's a set of procedures that can take different forms under the hood. It's similar to an array in that it's an ordered collection of data, but it means we don't have to worry about all of the nonsense every time we need to insert or delete something in our array. You can make a list with arrays. Sometimes it's called an array list. It's just another implementation. It has the same pros and cons as arrays. It's fast to access, it's slow to insert or remove items, but using the list interface saves us the annoyance of all that manual copying to make edits. An array list is a great data structure for things that sometimes change but don't change very often. If I had to guess, my Contacts app probably uses ArrayList to hold data it needs to display. It's pretty stable, so it wants the speed of an array list. You're mostly looking things up, but every once in a while you add a new contact, so it needs flexibility. Another implementation of a list is a linked list. A linked list is a variable that points to something, but instead of a single block of memory, it points to a node. And each node contains one piece of data, like the letter T, and a link to the next item in the list. Linked lists can be arbitrarily long. They don't require a block of adjacent memory. Once you see how linked lists are put together, you can imagine all kinds of arrangements of links between nodes. They don't have to be a straight line or just link in one direction. There are a lot of cool things you can do with nodes and pointers to other nodes, but we won't go into them now. So let's talk about editing. All you have to do is make your new node, connect it to the old node, and erase the old link. That's fast. But it doesn't come for free. The variable that holds the list just points to the first item. Under the hood, you have something that says you are here. It keeps track of where you are in the list. And every time you need to go somewhere else in the list, it does what we call traversal. So it follows the node from one item to the next item, to the next item, to the next item, and so on. And all this takes time. So with a linked list, you can get to the front pretty much instantly, but it takes longer to get to items later in the list. The longer the list, the longer it takes to get to the end of the list. Still, no matter how long the list is, it is much faster to insert and delete than with an array list, because at least you don't have to copy the list every time. Linked lists are great in situations where your data is changing rapidly. If I were building an editor, I would probably use something like a linked list under the hood to hold the text as people were editing. So how can we get the benefit of the linked list without the cost? There's two things. They're pretty specific: a stack and a queue. A stack is built on top of a linked list, but it just pays attention to the front of the list, and it ignores everything else. When you use a stack, you don't think of it like a list at all. You think of it like a pile of things. You can push items onto the top, and you pop them off like it's spring-loaded or something. A stack is instantaneous. It can be arbitrarily long. It can be giant. It can be huge. You'd never know. You only access things in the front of the list. You'll often hear people throw around the acronyms FILO, which stands for first in, last out, and LIFO, which is last in, first out. FILO is what you'll hear more often. If you've ever used undo while editing a file, you've probably used a stack. Every change you make goes onto the stack, then undo pops them off, leaving you with the remaining stack with the item off of it. Queues are similar to stacks, except they have another hidden variable. They've got a front that points to the front, but they also have something that points to the end. Queues are also instant access. Like stacks, they can be arbitrarily long with no impact on speed, but you can't access any data in the middle. You can only take off the front, and you can only add on the end. You'll often hear people toss around the acronyms FIFO, first in, first out, and LILO, last in, last out. People will usually say FIFO. If you've ever shared a printer, you've probably heard the term printer queue. Queue is the data structure used for holding data being sent to the printer. It takes the first sheets printed first, it prints the last sheets printed last. Arrays, lists, stacks, and queues are some of the basic structures for dealing with ordered data. When you know how they work and what considerations are in choosing them, it will help you understand the kinds of things you might do with data and programs. Many modern languages have higher level data structures built on these structures. We'll talk about these in another video.